Let's take a look now at section 10.2 and talk about parametric equations. In trigonometry, you define sine and cosine of an angle theta by using the points on the outer edge of the unit circle. Your definition depends on a central angle in standard position, which we call theta, or any other symbol you like. And you know that if this is in standard position, meaning the initial ray is along the positive half of the x-axis, then the terminal ray will cross the unit circle, a circle with a radius of 1, at a particular point. That point, x comma y, can be used to define the cosine of the angle theta and the sine of the angle theta respectively. Cosine of the angle theta and the sine of the angle theta. Notice that here you have two different functions based off of a common point, of a common piece of information, an angle. Notice that those two functions give you a point in space. What I mean by that is I could give you an angle theta and tell you, okay, let's say the angle theta is pi over 6. Well, then from that one piece of information, you could find a point in space. Namely, the x value would be the cosine of the angle theta, or in other words, it would be root 3 over 2. And y would be the sine of the angle theta, which would be 1/2. Notice that that's a point in the plane. That's x comma y. So given one variable, you can find a point in a two-dimensional graph on the xy plane. This kind of variable is called a parameter. Okay? And the equations that tell us how that parameter can be used to find points in space are called parametric equations. Here, the reason I was able to give this number was because I know that x is equal to the cosine of the angle theta, and I know that y is equal to the sine of the angle theta. So here, this number is a parameter. These equations depend on that parameter, and so these are called parametric equations. We can use the parameterization of a curve to take advantage of some things which would normally not be doable for a particular curve. In particular, notice this is a circle. Okay, well, one of the things about a circle is that it is not a function of x or y. I cannot write this as y as a function of x or x as a function of y because, again, it's not a one-to-one operation. But notice that even though this circle doesn't display y as a function of x or x as a function of y, it does show both of these components, the x and the y, as functions of something else. So what you can do is you can take something that's not really a function, but separate it so that each of its coordinates can be thought of as a function. And since most of what we do through Cal 1 and Cal 2 depends on us starting with a function, so we can take a derivative or an antiderivative, that means that there's going to be a way of expressing things that normally are inaccessible to calculus in a way that makes them more accessible. All right, so this is section 10.2, and let's go ahead and give a definition. All right, let's start off with a couple of functions. Let f and g be functions of, here we're going to say t. T is going to be your parameter. T is a pretty common symbol for a parameter. Usually T stands for time. That's a convention from physics. Let's not worry about it. Let's just say for us, usually the parameter will be T. And here, let's even label that. Here, that's our parameter. On a particular interval I, then let's go ahead and have a couple of equations, have these couple of equations define the points on our plane. The equation x equals f of t and the equation y equals g of t. These are going to be our parametric equations. The set of points x comma y as t varies over I are going to form the graph of the parametric equations. And that graph is going to represent a plane curve. Right. So here's our definition. We're defining a few things. First of all, we're defining what a parameter is. A parameter is just a variable. It's a variable that's applied to two different functions. Those two functions, when taken with that parameter, give you the x-coordinate and the y-coordinate of a single point in space. So here, these equations are called your parametric equations. So a parameter, that's just that variable t. The parametric equations are the two functions of the variable t. The set of points, x comma y, that these give you, that's the graph of the parametric equations. And if you take together these equations along with this set of points, you form what's called the plane curve. So this is sort of a loaded definition here. So let's take a look at some examples at how we can interpret some plane curves. We'll start off with a straightforward and simple one without much trickery. And then the next two will show that they can get a little bit more expansive, but still behave very much the same way. So let's begin with an equation, rather with a set of equations. Let's let x be given by, let's say 5 minus 4t, and let y be given by 2 plus 5t. All right. So the question here is going to be, we're going to sketch the curve represented by this plane curve. So sketch the curve and remove the parameter. Okay. We'll talk about this one here once we get done with this one. So sketching the curve is pretty simple. We're just going to plot some points and see what happens. So here we're going to say, okay, look, t, we can choose whatever we like because t is a free variable. But once we choose values of t, that'll tell us what our x and what our y are. Okay, so let's see here. I'm just going to keep things simple. Let's start off with t is equal to 0. Okay, well, if t is equal to 0, that's going to be 5 minus 0, which is 5. And this will be 2 plus 0, which is 2. Okay, so if t is equal to 0, then that gives us the point 5 comma 2. And I'll graph all these at the end. If t is equal to 1, well, that'll be 5 minus 4, which is 1. And this will be 2 plus 5, which is 7. Okay? And I can say x is equal to t is equal to 2, and that'll give me 5 minus 8, which is negative 3, and then 2 plus 10, which is 12. Okay? Now, t can be any value we like, generally speaking. There's going to be some exceptions once in a while, but we could say negative 1, and that's fine too. If t is equal to negative 1, we would have 5 minus a negative 4, which is 5 plus 4. That would give us 9. And here, this would be 2 plus a negative 5, which is just 3. 2 plus a negative 5 would be negative 3. Okay? And of course, we keep going. We could find a bunch of values of t, but this should be enough to give us a sketch. All right, so let's take a look now. All right, so let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is just a matter of plotting a few points. Here, let's see. Note, these are the points, x comma y. The t does not give you a spatial dimension. So here we have 9 comma negative 3, so 9 to the right, and then 3 down. 5 comma 2, so 5 to the right, and then 2 down. 1, 7, so let's see, 1 to the right and 7 up. 1, 2, 3, 4, 5, 6, 7. And then negative 3, 12. So that'll be, let's see, 1, 2, 3, and then up 12. Just like that. All right, and, oh, that should be a positive 2. My apologies. That should be right 1, 2, 3, 4, 5, and then up 2. There we go. Not that one there. Okay, so we have a few points on our graph. And you notice that if you connect the dots, that does look like a nice straight line. In fact, that's exactly what this is. This is a linear equation. And in spite of the fact that this graph was drawn freehand, it does work out pretty nicely as a linear equation. All right, so that would be our graph. There is something here, though, that we don't usually have with a graph on a plane, and that's we have a concept of direction. Notice here, t. You can think of t as being time. When time is equal to 0, that means you just started looking at your particle. Imagine that this set of equations are telling you, okay, you have a little particle in space that's moving around. It's floating. All right, now, at time equal to 0, that's when that's the very first time you started counting. There's t is equal to 0. Now, if t is equal to 1, you can think of that as where is your point going to be 1 second in the future, or 1 minute, or 1 hour, 1 unit of time in the future. Well, there's time is equal to 1. T is equal to 2, well, that's going to be 2 units in the future. So here, this 0, 1, 2, 3, 4, 5, they don't tell you where on the graph you are. They tell you when you're at that location. You're at this location right now. You'll be in that location 1 second from now. You'll be in that location 2 seconds from now. You say, well, what about a negative? Okay, well, where were we 1 second ago? Time travel, right? We can look forward in time or backwards in time. T equals to 0 is now. Positive values of t are what's going to happen sometime in the future. Negative values are what has already happened in the past. So whenever we graph a parametric equation, we generally draw the sort of the direction of time, the arrow of the progression of time. This is called your orientation. It's sufficient to draw one little arrow unless it's a very complicated curve. Sometimes you'll have curves that go out and then come back, in which case you may have to draw different curves to make sure that you see what's happening over your entire graph. But anytime you have a parametric equation, you will have some form of orientation. Now, the second part of this question tells you to remove the parameter. What that means is, okay, this is a curve that we drew using these sets of equations. But you know, this is a curve on the plane just in its own right. Meaning I could just say, well, let's just take x and y. Why do I need the parameter t? Well, the parameter t is there to give you some information. It's there to tell you, okay, here's where I am now. Here's where I'll be in 1 unit of time. Here's where I'll be 2 units of time from now. Here's where I was a moment in the past. But if you don't care about the values of t, you could just describe this path without the parameter. That's called removing the parameter. Removing the parameter can be simple or complicated, and it all depends on what these equations look like. But generally, the way to do it is the same. You're going to pick one of these two and solve for the parameter. It doesn't really matter which one, although if there is a big difference between the way they look, you want to go with whichever one's simpler to solve for. But in this case, they both look simple enough, so I will pick this one and solve for t. Okay, so let's go ahead and remove the parameter. Step number 1, go ahead and take one of your parametric equations, doesn't matter which one, and solve for the parameter. So x equals 5 minus 4t. Let me go ahead and subtract 4 over to the other side. So x minus 5 equals negative 4t. Subtract the 5. Now let me divide both sides by a negative 4, and that'll give me t is equal to, well, if I'm dividing by a negative, the negative will become a positive, the positive will become a negative, and that's all over 4. Okay, so I took one of my parametric equations and solved for the parameter, solve for t. Now, you're going to take your other parametric equation, in this case y equals 2 plus 5t, and you're just going to take this and plug it right in. So this will give you y equals 2 plus 5 times 5 minus x over 4. And now we can simplify. Here we can distribute our 5. So that'll give us y is equal to 2 plus 25 minus 5x over 4. We can now take that. Let's go ahead and divide by 4 here. So this will give us y equals 2 plus 25 over 4 minus 5x over 4. And then those can be combined. 25 over 4 plus 8 over 4, that'll give us 33 over 4. So here we get y equals 33 fourths minus 5 fourths x. Or if you prefer, you can write it in the traditional y equals mx plus b form. Y equals negative 4/5 x plus 33 fourths. Which, if you notice, is exactly that same line right there. It's got a negative 5/4 as its slope. Notice from here I can go down 1, 2, 3, 4, 5. Right, 1, 2, 3, 4. So it does have negative 5 over 4 as a slope. And the y-intercept is 33 fourths, which is the same as 8 1/4. 1, 2, 3, 4, 5, 6, 7, 8, and just a little bit more. So that is, in fact, the same equation. But whereas this one has the time parameter in place, this one only gives you this path. It wouldn't give you an orientation, and it wouldn't give you which points exist at which time. All right? And here's your result. These two are the same line, but this one has the parametric information on it, the information about the parameter, whereas this one is just the line. Now, depending on your equation, this can be simple or maybe a little less simple. In particular, because some equations cannot be expressed in terms of just a single variable. Here we get y is a function of x. In some equations, that won't quite work out so nicely. Let's do another one here. We're going to go ahead and do the same question. We're going to sketch the curve and remove the parameter. Okay, let's consider the equations x equals to t squared minus, that'll be plus t squared plus t, and y equals t squared minus t, like this. Okay, t is a common parameter. Doesn't have to be t, it can be other letters, but you'll see t more often than any other. Go ahead and write your t's and your plus signs so that there's a clear difference here. It makes things very confusing to see t, right, or plus, plus, plus. Have some difference in your notation. All right, so here, go ahead and pause the video and give it a try. You should be able to sketch the curve by just plugging in values of t. You can choose whatever values you like. Simple, small numbers are usually pretty good. Plug in 0, plug in 1, plug in 2, things like that. And then try to remove the parameter. Right? Once you have an answer, go ahead and unpause the video and we'll go through it together. All right, so let's take a look here. We're going to have values of t, and those are going to give us values of x and y. Okay, let's start off with just t is equal to 0. I'm going to leave a little space here in case I want some negatives. All right, t is equal to 0. Well, that would make both x and y equal to 0. Okay, so that's going to go through the origin. If t is equal to 1, 1 plus 1 is 2, but 1 minus 1 is 0. If t is equal to 2, well, that's going to be 4 plus 2 is 6, and 4 minus 2 is 4. No, 4 minus 2 is 4. 4 minus 2 is 2. If t is equal to 3, that'll be 9 plus 3 is 12. And this will be 9 minus 3, which is 6. Okay. We could keep going, but that'll suffice. Just 3 or 4 points is usually enough for us to see a pattern. Here, let me do a couple of negatives, maybe just 1 or 2. If I use negative 1 here, that'll be positive 1 plus a negative 1, which is 0. And here this will be positive 1 minus a negative 1, which will be 1 plus 1 will give me 2. And if I use negative 2, that'll be positive 4 minus 2, which is 2. And then positive 4 minus a negative 2, which will give me 6. All right. And so now we can go ahead and graph this. Notice these are the same numbers but backwards. 2, 0, 0, 2, 6, 2, 2, 6. If you kept going, I think you'd find this would be 12, 6, and this one would be 6, 12. But it doesn't really matter. Here we have sufficient information to create a graph. All right, so let's go ahead and give this a try. Okay, my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Okay. So let's just start plotting. 0, 0, 0. Okay, so when t is equal to 0, we have the point 0, 0. Okay? And here I'll even label that's t is equal to 0. When t is equal to 1, we have the point 2 comma 0. Okay, so there's t is equal to 1. If we have t is equal to 2, we have the point 6 comma 2. So that'll be 5, 6 comma 2. And then 12 comma 6. So 12 comma 1, 2, 3, 4, 5, 6. Whenever t is equal to 3. And then we can go back the other way around. If t is equal to negative 1, so now we're going back in time, we're at the point 0, 2. And then when t is equal to negative 2, we have 2, 6. So 2 to the right, up, 1, 2, 3, 4, 5, 6. And that's t is equal to negative 2. So here we have a curve that's going this way. Something like that. You'll note that, again, our passage of time is going this way. Negative 2, negative 1, current moment in time, 1 second from now, 2 seconds, 3 seconds, and so forth. So this does keep going on forever, but it has a particular orientation. For a parametric equation, or for a plane curve, this curve is different from this curve. Even if they have all the same points, the direction being in the curve going in a different direction would classify it as a different curve. It will classify it as a different plane curve. So here's your sketch, and you get that just by plotting some points. Now, in the previous example, we removed the parameter by solving for t and just plugging in. That's kind of what we're going to do here, but you're going to notice that solving for t in these equations is just slightly harder. Okay? You can either brute force it, meaning, okay, well, I know a lot of algebra. I can solve for t here by completing the square. Or you can also try a little bit of trickery, meaning you can also try, even if you don't solve for t, you can solve for something that will substitute in its place. So, for example here, one simple way we could, well, the brute force way, the just straight out, let's just do this, complete the square. This will give you t squared plus t plus a quarter minus a quarter. You could then factor this, Move the quarter over and take the square root of both sides. Same thing would happen here. If you complete the square, that'll end up with the square root of y minus a quarter is equal to t minus a half. And then you can add the 1/2 over to the other side. So that would eventually work, but it just in the interest of thoroughness, before I do any problem on here, I work it out ahead of time, and the computation was not pretty, not at all. So that's why, since that computation was a little less than pleasant, I decided, well, maybe there's a cleaner way to do this. So here's an alternate way to do it. One way, of course, is complete the square and then extract the square. Same thing over here. Complete the square, extract the square. Whichever one you choose to do, once you extract the square, you'll get t is equal to something that involves x, or t is equal to something that involves y. Once you know what t is, plug it into the other one. If you find t as a function of x, plug it in right there. Or if you find t as a function of y, plug it in right there. But here's a slightly cleaner way to do this. And at the end, when we get our answer, we'll see why there are some complications to this one. You'll see that the equation is actually not a nice one, even if done a nicer way. So here, let's say x is equal to t squared plus t, and y is equal to t squared minus t. I've just rewritten those. All right, now notice that if I add these two together, I'm going to get x plus y is equal to, well, x is that thing right there, plus y is that thing right there. And if I do that, I get t squared plus t squared is 2t squared. And I get t plus negative t, which cancels out. Okay, so I get x plus y is equal to that. And instead of adding these, let's say I subtracted them. Okay, well, it's going to be the same thing, but now instead of a plus sign here, I'm going to subtract them. That's x minus y, minus y. Okay, well, if I do that, t squared minus 2t squared, that goes away. And I have minus a minus, which makes that a plus. So really, that's just t plus t. That's 2t. Okay. All right, well, now I can write that by saying, well, look, let me just divide both sides by 2. And now I get 2. I guess I get x plus y over 2 is equal to t squared. And over here, I get x minus y over 2 is equal to t. Okay. All I did was I divide the 2 over this way to give you that. Divide the 2 over this way to give me that. But now notice, if I square this, I'm going to get this. If I get that t squared is equal to t squared, which of course it is, obviously, right? Well, t by itself is x minus y over 2. But if I square that, I'm going to get t squared, which is x plus y over 2. T squared equals t squared equals t squared. Oh, but now this is nice. I can go ahead and square everything out over here. X minus y squared is x squared minus 2xy plus y squared. 2 squared is 4 equals x plus y over 2. And finally, since I don't like fractions, let me go ahead and multiply both sides by 4. So if I multiply now both sides by 4, that goes away. And I'm left with x squared minus 2xy plus y squared equals x plus y. Just like that. Oh, wait, no, I don't. I divided wrong, didn't I? Here, 2 goes into 4 twice. So now this 2 would distribute. So this will give me 2x plus 2y. There we go, just like that. And now here, there's our equation. That's the reason why it was not quite so simple to solve for t over here, because over here, it's not so simple to solve for either x or y. meaning here you can't really write y as a function of x or x as a function of y. There are ways, but it gets complicated. However, here we would get x squared minus 2xy plus y squared minus 2x minus 2y. Gone and subtracted that stuff over this way is equal to 0. From Cal 1, you may remember the name of these. These are implicitly defined equations. Implicitly defined functions. So it may not be possible to explicitly write the equation without a parameter, but it can be done implicitly. And in fact, here it is. Here is the graph of the implicitly defined equation, x squared minus 2xy plus y squared minus 2x minus 2y. It looks like this. It's almost parabolic, isn't it? And it's been rotated a bit. For those of you who remember their pre-cal very well, that's you'll remember the rotation of conics. You'll remember taking a conic and being able to rotate it a certain amount. That's what we have here. But in any event, you see the shape of this curve. And you'll notice that it is reflected in the shape of this curve. It is the same thing. All right? Okay, so we see two examples of sketching a curve and removing the parameter. Let's take a look at just one more example, in particular because this example is going to use something that's very common, and that's going to be using a little bit of trigonometry and some trigonometric identities. Don't worry, it's not quite as complicated as it sounds. Let's consider something like, x equals 3 times the cosine. So here, same kind of equation, same kind of thing. In fact, here, let's not even worry about sketching it. Let's just say, let's remove the parameter. Right? Because sketching it is, well, going to work the same way every time. You're going to plot some points, connect the dots, and make sure that you have your orientation. Make sure it follows the arrow of time. Time goes forward. Okay, so let's remove the parameter, and let's take our equation to be x, or rather our equations, we need two of them, to equal 3 times the cosine of the angle theta. And we want y to equal to 7 times the sine of the angle theta. So I mentioned before that t is a very common parameter, but it won't always be t. In fact, with trigonometric parameters, you'll often see theta. So you're not parameterizing with respect to time, you're parameterizing with respect to an angle. All right, so let's go ahead and take a look and see how that should work out. Normally, we would say, okay, solve for the angle theta, or solve for the parameter, t or theta or whatever. But in this case, you'll notice that's a little complicated. I could start off by dividing both sides by 3 here, and that would give me x over 3 is equal to the cosine of the angle theta. Same thing over here. I could divide both sides by 7, and that would get me y over 7 is equal to the sine of theta. And so far, that's nice. But now, if you were trying to isolate the angle theta, the next thing you'd have to do is take the inverse cosine of both sides. Or over here, take the inverse sine of both sides. And that is something you can do. We've all taken trigonometry. We know how that works. But we also know that that's going to open us up to some unpleasantries. In particular, sine and cosine's inverse function, the inverse sine, the arc sine, or the arc cosine, have restrictions on their domains and ranges. We also note that if you take an inverse something and plug it into a something, well, then we have to worry about how to simplify that. We know how to do that. That's something from trigonometry. But it's also somewhat involved. It takes a bit of work, and it does leave you prone to making a mistake here or there. Here, we're going to use trigonometry, but not the inverse operations. Here, we notice a simpler way to do it. And here's a way that you're going to want to notice, because anytime you see parameterizations, this is something that occurs fairly often. Let me square both sides of this. If I square both sides, I'm going to get cosine squared of the angle theta is equal to x squared over 9. All I've done is I've squared this and squared this by squaring the top and then squaring the bottom. Same thing over here. I'm going to get sine squared of theta and that will equal to y squared over 7 squared, which is just 49. Well, now, let's add these two together. If I add these together, well, let's see. Cosine squared of theta plus sine squared of theta. Well, let's see. Cosine squared of theta was x squared over 9 plus sine squared of theta was y squared over 49. Oh, but from trigonometry, yeah, over here I was talking about trig identities. Here's a much simpler trig identity. This is the Pythagorean identity. The sum of the squares of the sine and cosine of the angle theta are just the number 1. So here we write this as 1 is equal to x squared over 9 plus y squared over 49. And you'll remember this as, you say, well, look, that looks like a circle, right? X squared plus y squared is equal to r squared. Well, yeah, but now I have these extra constants here which are deforming my circle. Oh, okay. I remember this from pre-cal. This is an ellipse. And now let's take a look at the other direction. So far, we've seen parametric equations where we eliminate the parameter, and then we maybe sketch the graph, or maybe we don't. What if we want to go the other way? What if I have just a regular equation and I want to parameterize it? That's usually fairly straightforward. It kind of depends on what the equation is, but generally, it's not too complicated. Here, let's say, let's go ahead and find two parameterizations, just so we have a couple of examples. Of the curve y equals x squared. Okay? So when we say two parameterizations of this curve, you say, well, how do I have two different answers? Well, note, this curve is considered distinct from this curve, going backwards. So you may have curves that trace the same, you may have parametric equations which trace the same curve, but if they're going in opposite directions, they are considered two different parameterizations. So that's kind of what we're saying here. We're saying, okay, I know that I could sketch that curve. It's a very simple parabola. In fact, it's the most simple parabola. It's the one that passes through the origin. All right, well, that's a curve. There's no parameterization there. We want to introduce a parameterization. We can introduce two different ones by having one start from here going this way, and we can have another one start from here going this way. In some more advanced applications, you may have one that starts simultaneously here and here and goes out, but that's not something we're going to be looking at right here. So here, let's consider one parameterization. There's going to be a few cases where your parameterization can be more complicated, or maybe should be more complicated. But for most parameterizations, and especially any of those that are y as a polynomial function of x, generally what you want to do is you want to just take your independent variable, your x, and just call that t. So here, let's say parameterization 1. Let's just go ahead and take our independent variable, take your x, and just call it t. Yeah, there we go, x is equal to t. Okay, well now what? Well, we know y is equal to x squared, but x is the same as t, so we just say y is equal to t squared. And there we go, there's a set of parameterizations. I have x is equal to something that involves your parameter. Separately, I have y is equal to something that involves your parameter. And that's what that is. So although there are some more complicated ones that can happen, usually the most simple one is to take your independent variable, just call that t. Here, x, just call it t. And once x is equal to t, well, you say y is equal to x squared. Well, yeah, but y is the same, x is the same as t. Okay, so just say y is equal to t squared. And there we go, that's a parameterization. Parameterization number 2. Again, there are other ways to do it, but the simplest way is to say, well, look, if here x is equal to t, as x moves to the right, time is going forward, right? As t gets bigger, x goes to the right. Well, what if I want to trace that same curve but going backwards? Oh, okay, we'll now have have x equal to negative t. Because now, as t gets bigger, the negative t will get lesser. It'll go this way. So this one would trace things to the right. As a negative, this would trace things to the left. Oh, okay, but now if x is equal to negative t, y is equal to x squared, or in other words, y is equal to negative t squared. Oh yeah, but squaring a negative makes it a positive anyway. So here we just write this as y equals to t squared. And there you go. These are two different parameterizations. X equals to t, y is equal to t squared. Here x equals to negative t and y equals to t squared. And they both cover the same curve. They both give you this curve when you parameterize them. If you were to now start plotting a bunch of points for this one and this one, you would note that they both cover this, but because they're traveling in different directions, they are considered two different parameterizations. And that is it for this section. So if, well here, let's give an assignment for the section. To practice the things that we've talked about here, try section 10.2, 5 through 21 odd, 35 through 45 odd, and then try numbers 51 and 53. And that should suffice, section 10.2. If anybody has any questions or problems, make a note of them and reach out to me, and I will get back with you as soon as I can. And I hope everyone has a nice day.